Welcome to Lesson 7. In this lesson, we are going to study Python's support for iteration. We have learned that loop structure is one of the three basic structures of structured programming. We also learned how to create an infinite loop and use the break and continue statements to control the iterations of the loop structure. Python has rich built-in support for iterations. In general, Python supports the following loop structures: while loop and for loop. While loops. While loops are indefinite loops. The syntax of while loop is as follows. While condition. Loop body. The statement causes the interpreter to run the codes in loop body repeatedly, as long as the condition is true. Example. The code fragment here demonstrates data validation. The purpose of the code fragment is to capture the user's response to a question. The expected answer is either Y for yes and N for no. However, the user may not enter a valid answer. In the code fragment, the data validation logic uses a while loop to ensure that only valid answer from the user is accepted. The variable question stores the question that will be shown on the screen. The variable answer key stores the expected answers. The variable prompt stores the combined question and answer key. The prompt is shown to the user. Capture the user's input. Convert the user's input to uppercase answer. And store the capitalized answer. The continuation condition of the loop is answer not in the list of Y and N. If the continuation condition is true, the loop body prints the error message. And repeat the prompt, input, check, repeatedly, until the continuation condition is false, which means the user's answer is Y or N. The remainder of the code fragment converts the validated answer to Boolean data, true or false. This is a sample execution of the code fragment. Exercise. Compare the following conditions. Answer not equal Y and answer not equal N. Answer not in the list of Y and N. The first condition uses mathematical logic connectives, and, or, not, operators. It can be used to express any conditions, but it is hard to read and maintain. The first condition uses mathematical set membership operator, in operator. It is easy to read and maintain, but it cannot be used to express general conditions. Exercise. Change the codes to accept the following forms of answers in a case-insensitive way. Y, yes, and no. Here are the changes. 1. Answer key equal Y, yes, N, no. 2. While answer not in list of Y, yes, N, no. 3. If answer in list of Y, yes. Exercise. Write the data validation logic as a function. This is how the caller may call the function. Yes/no predicate, do you have a fever? This is the expected return value. True if the user says yes. Else return false. Here is the sample answer. The first statement defines the function. Gives it the name yes/no predicate. The function takes a parameter named question. The loop body prepares the prompt from the question. And repeat the prompt, input, check process. This statement calls the function, with "Do you have a fever?" as an argument for the parameter question. This is a sample execution of the codes. Loops with else clause. A unique feature of loops in Python is the else clause. The behavior of a loop with else clause is as follows. If the loop terminates normally, the else clause is executed. If the loop is forced to terminate by break statement, the else clause is skipped. This is an example of a loop with else clause. The codes control a typing training session. After printing the guidelines, the program goes into the input, process, output, cycle. The program uses a counter, named count, to keep track of the number of lines in the typing session. If the count hits 3, the loop terminates normally, and the else clause is executed. Here is the sample run that demonstrates this test case. Another way to get out of the loop is to enter the title sign character, In that case, the program breaks the loop after printing an appropriate message. In this case, the else clause is skipped. Here is the sample run that demonstrates this test case. For loop, definite loop. The while loop is great. But there are many simple iteration tasks, which require a definite loop, which traverse, iterate or walk, through a container, and process each object exactly once. The following code template. Template A. Demonstrate how such traversal of a container can be realized by using a while loop. Let's container be any compound structure such as string, list, set, etc. The loop continuation condition is: the container is not empty. The loop body gets the next object in the container and visit the object, which will process the data represented by the object according to the business logic of the problem domain. Problem. The programmer needs to know the iteration logic which is in red. Can we do away with such iteration logic so that we can concentrate on the business logic of the problem domain? The answer yes. And the solution is to use definite loop structure. The for a loop, as shown in the code template B. Again, let's container be any compound structure such as string, list, set, etc. The for loop asks for the next object in the container and store the object in the variable O, B, J, if any. Otherwise the loop terminated. The loop body concentrate on the business, namely, process the next object in the container. The advantages of this code template are: 1. The code template is shorter. 2. The code template is cleaner. 3. The iteration logic is performed by the container itself, implicitly under iterator design pattern, which makes use of the concept of iterables. An iterable is an object that is able to return its members one by one. In other words, an iterable is a compound container that a program can iterate over with a for loop. Any iterable can be used in place of the container in the code template B. In the code for loop 1, the iterable is a string, and the element of the iterable is a character. The loop concentrates on processing the element of the iterable. In this case, is to check whether the character is a vowel, and print the character accordingly. In the code for loop 2, the iterable is a list, and the element of the iterable is a string. The loop concentrates on processing the element of the iterable. In this case, is to compute the total length of all the strings, and print the total accordingly. In the code for loop 3, the iterable is a dictionary, and the element of the iterable is a pair. The key represents employee, and the value represents the monthly salary. The loop concentrates on processing the element of the iterable. In this case, it is to add 500 to the monthly salary for each employee. Behind the scene of for loop, the system has done a lot of work. For such a simple for loop structure, the system converts into the following 8-line codes, using indefinite while loop structure. Line 1 defines a Boolean variable, more element. The Boolean variable will be used as the continuation condition for the indefinite while loop. This variable is initialized to true. It will change to false here when the exception, stop iteration, is raised. Line 2, get an iterator from the iterable through the use of iter function. An iterator is sort of a finger. The finger is pointing to the position before the first element in the iterable. We can ask the finger to move to the next element in the iterable if any. Line 3 to line 8, form an indefinite loop, the while loop. The loop body starts with a try, except block, and then followed by the main business logic. In the try block, we ask the finger, iterator, to move to the next element, if any, and store the element in the variable, an element. If there is no next element, the finger will raise an exception called stop iteration. The except statement will catch the exception and turn the loop continuation condition, more element, to false. Here is the sample loop 1, written in an indefinite while loop instead of the definite for a loop. Study the codes. Concentrate on the iterator design pattern. Execute the codes and observe the outputs. Pause this video and do it. Ranges. A range is iterable that can be used to provide a sequence of numbers. By specifying the begin, end, and step value for the sequence. An interesting fact is that a range is a lazy iterable. A range object stores only the begin, end, step, current value. No sequence of numbers is maintained internally. It computes the next value of the sequence on demand. Therefore, a range object is an extremely lightweight iterable. Code explanation. Line A1. The code fragment creates an object of type class range through the range function. Line A2. The range object plays the role as an iterable in the iterator design pattern, as shown in the while loop. Line B. The range object can be converted to other iterables, such as lists or tuples. The codes for iterating a range and other iterables are similar. While the range is a lightweight iterable, the tuple is a heavyweight iterable. The tuple stores all the elements in the sequence. The code fragment here shows 4 different ways to create a range object. In general, a call to create a range object takes 3 parameters: range, begin, end, step. If step is missing, the default value is 1. So range 0, 5, is the same as range 0, 5, 1. If begin is missing, the default value is 0. So range 5 is the same as range 0, 5. The step value can be negative. For example, the list range 5, 0, minus 1, is the same as the list of 5, 4, 3, 2, 1. On receiving the next message, the range will move the current value to begin. Begin plus step. Begin plus 2 times step. Begin plus 3 times step, etc. When current value hit or go beyond the end, a stop iteration exception is raised. A range represents a linear sequence of numbers, such as 1, 3, 5, 2 times I plus 1. If a nonlinear sequence is needed, we can use a generator. For example, we can use the following generator to generate a quadratic sequence. I squared for I in range 10. Note that I star star 2 means I squared. The generator uses the range function to generate a linear sequence, 0, 1, 2, to 9. And convert each element I to I squared. The result is the following nonlinear sequence: 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Optionally, the values in the sequence can be filtered by using a if clause, such as if mod 2 equals 1, which mean I is an odd number. So overall, the generator I squared for I in range 10 if mod 2 equals 1 specifies a lazy iterable sequence: 1, 9, 25, 49, 81 inches. List comprehensions. The syntax for generator expression defines a generator, which is a lazy iterable sequence. Note that a generator can be used to iterate through the lazy iterable sequence only once. In other words, once a generator has reached the end of the iterable, there is no way to reset it to the beginning, unless we reuse the generator expression again. If such behavior is not desired, we can use a list comprehension to define a list for the same sequence. A list comprehension can be constructed by including a generator expression in square brackets. Study the codes in the output of this code fragment. 1. Line A generate, via list comprehension, a list, which is a heavyweight iterable. 2. Line B create a lightweight iterable, via a generator expression. 3. The list can be reused for other purposes without regenerating the elements. 4. Once a generator hits the end, it behaves like an empty sequence. 5. We can recreate the generator through the generator expression again. This is the end of Lesson 7. Thank you for your participation.